Good afternoon. We were discussing two-stage op-amps. In particular, to have a type of output stage where you can have a bias current to be smaller than the maximum load current. Okay. So the standard class A biasing is to make sure that the bias current is more than the worst case or the maximum load current, so that you can supply that much current. This can lead to a great deal of inefficiency because I mean, especially with very heavy loads. And if you have a very heavy load that is infrequently used, it means that you're constantly drawing a bias current that is more than the maximum load current all the time. But actually, you're driving that load current only a small fraction of the time. Okay, so that is the motivation for what is known as class AB biasing. There are many ways to do it. Basically, the bottom line is somehow you have to ensure that you have two output transistors. Let's say M11 and M12. In class A biasing, one of them will get a fixed bias so that it acts like a current source, and the other one gets bias plus signal. Now, if you want the current to vary in both transistors, the signal must appear in both of them. Okay, so that is one part. That by itself is easy to arrange. You can just connect the two together, but that introduces other constraints. And you can do AC coupling for one of them and so on. But if you don't want to do any of that, and you would like a well-defined bias current in the output transistor, so first let's start with a slightly complicated current mirror biasing, right? So what we do is the following. So we have a source follower also driving that. Okay. And then to bias this, let's say we have that one. So let me call this okay, and this is M22X, M12X, and similarly here on this side, this is M21X, M11X. The corresponding devices have the same current density. They are replicas of each other. That's the idea, right? I hope you understand what I mean by current density. They will have the same length and they will have the same current by width. Okay, this is just like in a current mirror. They need not have the same current, but they'll have the same current by width, so that they'll just be replicas of each other. They'll be operating with the same VGS minus VT. Okay, so instead of writing out the equations and so on, by now you should understand what this means. M12X and M12 are replicas of each other. That means they are designed to have the same VGS minus VT. Okay, and some current. So finally, you can adjust the size ratio so that you get the desired bias current in the output. Similarly, M22X and M22 are replicas. M11X and M11 are replicas. M21X, M21 are replicas. Okay, and I'll just show a single bias current source. You adjust the current and the sizes so that you get whatever quiescent current you want in the output branch. Okay. So now let me start off with this connection. I'll connect this to VDD and I'll connect this to ground. Okay. If I do that, what is the impedance looking into the source nodes of M21 or M22? What is the impedance looking into the source of M21? 1 by GM21. So here it is 1 by GM22. Okay. So it is a, you can try to couple a signal to the gate of M11, but now you can see that there is a small resistance from there to ground. Okay. So if I now connect my usual single stage op amp, its output to that node, what happens? So let's say I do this. Okay. That's how it was earlier, right? I mean, I didn't have all this elaborate bias circuitry, but I had this going to the gate of M11 and then I had a fixed bias current M12. So if I do that, first of all, what happens? If I do this, what will happen to the, will the op amp work as expected? What is the issue? Huh? So that 1 by GM21 loads the first stage. So the first stage gain goes to pieces. Okay. So I'll just come back to the problem I had given in one of the older assignments. So what is done is the following. This is connected there and this is connected over there. Okay. So that is the circuit you had analyzed. Okay. So in that case, what happens is, what will be the impedance looking into this? Whatever current goes here comes back through that. Okay. So what is the impedance looking there? It is infinity. Okay. So basically it is not loading the previous stage anymore. On top of it, this current goes this way, goes through this GM. Whatever incremental voltage is here will also appear at the gate of M12. Okay. So this is called a class AB or a push-pull output stage. Normally what would happen is, if the output of the first stage went up, the current through M11 would reduce, the current through M12 would be the same, would be constant anyway, it was a constant current source. So a current would be drawn from the output. Now what happens is, if this increases, the gate of M12 also increases. So both of them, the current through M11 decreases, current through M12 increases. Okay. So you get the combined GM of the two, and there is no limit on the current. It's not limited to the quiescent current. You can get higher than the quiescent current from the output. Okay. So this is the class AB output stage. You can just try to understand it. It's a little involved, but people have come up with it for some reason, basically to be able to deliver currents that are beyond the quiescent current. Okay. Which one? Oh yeah, this one. All right. Yeah, the biasing direction was reversed. Thanks. It should be that. So this was quite popular. The only thing is that it is a little difficult to get this to work with low supply voltages, so many stack transistors. It can be difficult. Okay. Any questions on this class AB biasing? You can also try to come up with these things, right? The basic principle is, you have two devices. Class A bias, one side is fixed, only other side current varies with the signal. Class AB means both sides vary with the signal. If the upper one increases, the lower one decreases, and vice versa. That's all. So any bias arrangement that you come up with which achieves this will also work. Any questions on this or any aspect of the single stage op amp? Yes. Currents more than the bias current. Yeah. So normally there will be, so in class A, what would happen is, this is M11 is biased at some VG11 and M12, its gate is biased at some VG12. Okay. And the total load current is I11 minus I12. Okay. Now you add signal only to one side, right? So what happens is that, of course, if you don't add any signals at all, the two currents are fixed and there is nothing varies. If you add signal only to one side, you can change the current on this side. Okay, you can increase and decrease it. But how much can you decrease it? Increasing, of course, to push current out, potentially you can do a lot. So you can push I would say unlimited currents out. It's not quite unlimited because Vx is also limited, but you can push a lot of current out. But how much current, how much negative IL can be there? The most you can do is I11 equal to 0, right? You can just cut this off. Then you will have I12 to be minus IL, that's all. So that is the maximum you can pull in. If you apply Vx only to the bottom side, then how much you can push out will be limited. Okay. So the way to get around this limit is to add a signal to this side also. Okay. Then to pull in current, for instance, you don't just cut this off. You're also increasing the current through M12. So you had some current when Vx was 0, that is the quiescent current, but you can actually pull current more than that. Okay. So that's how you can have load current in both directions to be more than the quiescent current. Any other questions on this or any other aspect of the single stage op amp? Yeah. Right. No. This is to, so we have put two conditions. We have said, see, early on we determined, like long back in analog circuits, that it is good to have a known current biasing through the MOS transistor, right? Because it is less sensitive to, GM is less sensitive to transistor parameters. So we want to have a known quiescent current. Okay. Otherwise, you can just tie some voltage there and then be done with it. So that's why we have this. It's basically a current mirror, somewhat fancy, so that we also can add a signal to that. Correct. So that I mean, this connection, this is to make sure that you get infinite input resistance as well as you get the same signal there and there. Okay. Without that cross coupling, that won't happen. Anything else? Any other questions on single stage op amps, single ended op amps? Any single ended, not single stage, single stage or multi stage single ended op amps. By single ended op amps, I mean differential input, single ended output with respect to ground. Yeah. What is that? No. I mean, it can be scaled versions, right? Normally, you don't waste, if you have a current mirror, this branch will be a scaled version of this. If you want like a 10 milliamps here, you won't be wasting 10 milliamps in the current source. You may use only 100 microamps and then multiply it by a factor of 100. You make sure that the lengths are the same, and this is, and again, that ratiometric layout I have talked about. You use some unit elements and you use as many unit elements here as required. That is, if you want a 1 to 100, you may use 2 fingers here and 200 fingers there and so on. Okay. So you don't always, I mean, 1 to 1 is not always a good thing, because I mean, what is that doing? That is just like sinking current, doing nothing. Okay. So this is a replica of this. So first of all, the main output branch is that one. So let's say you want, I don't know, pretty large current, 5 milliamps through that. So you may put 5 milliamps through this one. Through this branch, I mean, I'm just like pulling some number out of the hat. It could be 500 microamperes. But these branches could be taking only 50 microamperes or 100 microamperes. But you just make sure that the size ratio is appropriate. That's all. Well, the way I have written it, I mean, it's the same current flowing through this. So the ratio of these two and ratio of those two have to be the same. And similarly, the ratio of these two and these two have to be the same. But if I use some other, I mean, it doesn't have to be like this, right? I could have that and that. I mean, there's no particular reason to do it, but that's how it will be in practice, I suppose. If those two currents are different, then the ratios will be different. Anything else? Okay, I think we've had enough of single-ended op-amps. Basically, a single-ended op-amp means that there is this ground, and then you have two voltages, V1 and V2, with respect to ground. The op-amp ideally responds only to the difference V1 minus V2 and gives you a voltage VO with respect to ground. But we know that, of course, it's not going to respond only to the difference. It also has a response to the average. We know that V0 is the differential gain times the differential voltage plus the common mode gain times the common mode voltage, where the differential voltage is V1 minus V2 and the common mode voltage is V1 plus V2 by 2. Okay. So this is a single-ended op-amp. Now, what is preferred on integrated circuits are fully differential structures. That is, for every signal, you use a pair of wires, right? The two voltages, for instance, on the wires will be equal and opposite. That is what is fully differential signaling. Why do we use this? What is the point of this fully differential stuff? You have encountered fully differential before in analog circuits? What are you aware of? So why do we use? Okay. So if we, let's say I'll just write fully differential signals, and to process them, you use fully differential circuits. What does it mean? Any signal Vx, you use two wires to represent them. The desired signal Vx will be Vxp minus Vxm. And if you had currents, that would be the same. Okay, you will have equal and opposite currents in the two wires. Okay, so this is in contrast to when we say single-ended. What does it mean? You have a number of, I'll show voltages, but the same applies for currents also. You have a number of voltages. Voltage is always a difference. Okay, but we specify only one node. What we mean is that basically the voltage signal is the difference between that node and the common reference node. Whereas in when you have fully differential signaling, we dedicate two wires for each signal. Okay, two nodes, and your signal will be measured as the difference between them. I mean, the significant part is not measuring the voltages different. Voltage is always a difference between some two node voltages. Okay. Only thing is here, we also want the voltage on each wire with respect to the common ground to be equal and opposite. That is, if you want a sinusoidal signal, you would like the two sinusoids to be that way. Okay. Why do we do this? Is there any usefulness to this? Huh? So what happens is the following. So let's say you have single-ended circuitry. Okay. Of course, each stage has some output voltage and it will also drive some current. Okay. And these are the supply rails, not normally shown when you're only showing the functionality, but of course, very important. Right. So now I can be a little more explicit and say that let's say the output of this voltage, output voltage is available between its output node and this negative rail. What the following stage senses is between these two, okay, or it could be between those two also. For instance, if you have an NMOS common source amplifier, the source would be tied to the lower rail. What is the NMOS common source amplifier sensitive to? Voltage between the gate and the source, that is between its input terminal and the lower rail, assuming the source is tied to the lower rail. If it was PMOS, it is sensitive to the voltage between here and the upper rail, because the PMOS source would be tied to the upper rail. Now we assume that the upper rail and lower rail, their difference is a constant, because we have the supply voltage, ideal supply voltage with zero resistance. Okay. Also, a stage will drive a current to the following stage. Okay, depending on what stage it is, the current can be small or large, but it will drive. I mean, that's how it propagates the signal. But I have said current always travels in loops, right? So where does that current go? So this current, it's very easy to show it like this, but where does it go? So basically, it can do many things. It depends on the internal details. But finally, a part of it go that way, part of it could go that way, and then somehow finally all of it has to form a loop. Okay. Now, if you look at these supply rails, there will be currents from various stages flowing through them. Okay. Now, of course, no wire is perfect. So you can have inductances and resistances on all these lines. Okay. Now you can see what happens. The current flowing through this impedance will cause some voltage drop across this. So the voltage input available at this stage is not just the voltage output of the first stage plus whatever drop is there on that one. Okay. So you have some voltage from this, some voltage across that, the two together will appear there. And it may not always be easy to predict how much drop you will get there and so on. Okay. Because the actual current flowing through the supply rails is not only because of this stage, it could be because of other stages, many things that are connected together. And exactly how the current splits, it's also not always clear. Okay. For instance, it could be that if the current output here is a sinusoid, the current drawn here is a sinusoid. That is one possibility. Another possibility is the current here is a sinusoid. The current in this rail is half of a sinusoid, that is halfway rectified. The current in the bottom rail could be the other half and so on. In fact, they are even non-linear. That is, while the actual voltage, intended voltage and currents don't have any harmonics, the currents drawn from the supply rails can have harmonics. Okay. Ideally, in fact, this is, I think this problem you must have seen before, that if you just draw a standard opamp amplifier circuit, okay, there is apparent violation of Kirchhoff's current law, right? Because Kirchhoff's current law applies not just to nodes, but to any closed surface, right? So now if I draw a closed surface around the op-amp, where is Kirchhoff's current law? Current is coming out of the output terminal, but nothing is going into the input terminal. So what's happening? Where is the current? Through the supply. So now exactly how this output current, how these currents, let's say I plus and I minus, depend on the output current, it depends on the construction of the op-amp. So in the ideal class A case, what happens is one of them will be fixed, the other one will just supply IL. Okay, the difference between these two is IL, right? Assuming there is no other current, there will also be some fixed bias overhead. In the ideal class B case, any current that is pushed out will come from the upper rail, any current that is pulled in will come from the lower rail and so on. So the current itself can have a very complicated waveform. So what really happens is if you have a large circuit, there are all these parasitic drops in the supply and ground impedances. So what that will do is it will cause these parasitic drops. So if you are coupling one stage to the other, the idea is the output of this stage is the input of the following stage. But usually the input of the following stage is the output of this stage plus some garbage which is related to all these currents that are flowing, supply impedances and things like that. Okay. In fact, it's to avoid this that you use things like bypass capacitors, okay, on each stage and so on, if possible, so that then this will provide a low impedance path directly here. Make sure that this node and that node are very close to each other in their voltages and provide return paths for current, etc., etc. Okay, but this is a risky thing. Whenever you have single-ended signaling, you have all the voltages defined with respect to the reference node. Okay, and the return paths of the currents can be either the reference node or the upper rail. It depends on how the circuit is constructed. So it is to avoid this that we have fully differential circuitry, right? We know that voltage is measured as a difference between, difference of voltages on at two nodes, right? So for every signal, you just dedicate two wires. Instead of saying one wire, I will use it common. There is some merit to using a common wire. It is economical, right? Then for every signal, you have the reference node. Once you have that, for every signal, you use only one node. Whereas fully differential, that way is uneconomical. That is, for every signal, you are using two nodes. But you don't have this problem of sharing the common reference node. Okay. So in fully differential signaling, and ideally, the two node voltages are equal and opposites of each other, and one of the wires serves as the return path for the other wire. That is, if a current is pushed out in one wire, an equal current comes back in the other wire. Okay. So that way you are not sharing any common paths. That also is clean. Okay. So then you are much less susceptible to these parasitic drops across the power supply and so on. Okay. So this is the motivation for using fully differential circuitry, and it has other advantages as well. So for instance, if you just have two wires crossing each other, okay. So in cross section, it may look like this. This wire may be on a higher layer and the other wire may be on a lower layer. Now what happens is, of course, you have parasitic capacitance between there and there, and some parasitic capacitance from between there and there. Okay. So now, if I have Vx here, what is the voltage on the other wire due to Vx? Some voltage division depends on the parasitic capacitor. This will also get Vx times C1 by C1 plus C2. Okay. Now we can consider two scenarios. So let's say I have Vx by 2 and minus Vx by 2, and I have a wire crossing. And of course, when we say differential, it's not just enough to have two wires. You can't have this wire like 10 centimeters long and this wire 1 centimeter long. They are also assumed to be physically symmetrical. Okay, the physical layout has to be symmetrical. So that means that if this is C1, this will also be C1, and then of course you have C2 from here to ground. What is the voltage that appears on this wire? What will be the voltage that appears on that wire here? You have Vx by 2 times C1 by C1 plus C2 minus Vx by 2 times C1 by C1 plus C2. So this is basically 0. So if you have fully differential signal, again fully differential automatically means also physical symmetry between the two halves. Okay. So it will put out less garbage onto other signals. Okay, the crosstalk will be smaller. And similarly, let's say you have a single wire, but you are measuring Vy as a difference between these two, and again there is symmetry. What will be Vy? What will be Vy? U to Vx. What is the, so Vx has the same, Vx produces the same voltage on the two wires. So if you measure differentially, the effect is 0. Okay. So fully differential signal puts out less garbage, also takes in less garbage. Okay. It is, it doesn't inject as much interference. It's also less prone to interference because any common interference will get cancelled out. So if you have fully differential signals everywhere, these are the advantages you have. Okay. And this applies to everything. I have shown just wires crossing each other. You have all the signals on a common substrate. So what happens is, because of the parasitic capacitance between the wires and the substrate, actually currents will be going around in the substrate. But if you have differential symmetry, right, physically symmetric lines carrying equal and opposite voltages, then it will put out less currents in the substrate because the two will cancel out. Okay. So then from all points of view, this fully differential stuff is better. Only thing is now, of course, that you have to use fully symmetrical circuits. It's almost like doubling it. Okay, doubling the number of wires and so on. On an integrated circuit, it doesn't matter. What matters is the total area. Okay, not the number of components. On a discrete board, it may be the opposite. Okay, because the number of components, it will increase the cost. It will also increase the complexity of the board. Whereas on an IC, the fully differential circuit actually simplifies the circuit design. So it's almost always used. On a board, maybe you use it only when necessary. And typically, as you go to higher and higher frequencies, all these other effects starts becoming more and more annoying, and you may have to use fully differential signaling. Okay. And this applies to everything also. If you have a single wire running and it's carrying a current, what will be its magnetic field? So something, I mean, I'm sure you vaguely remember some formula from some time. There'll be some magnetic field rings around it. Okay. But then if I have two wires closely spaced to each other, and that is carrying I and it is carrying I, what will be the magnetic field around that? So you know from all those integral formulas that what matters is the total current enclosed. So if you have wires almost coincident and they are carrying equal and opposite currents, then the magnetic fields will cancel out. That's why also when you have these kind of wires, right, there will be a wire going this way and a return path. They should be very close to each other. Okay. I don't know if I have that old slide here. I have something to show. So if you want to, anywhere you make connections, things have to be like this. Let's say you have power supply wires and you have something like that. This is not a good thing. Okay. The way to connect wires would be, you should take these two and then maybe twist them together so that they don't enclose a large area. Okay. So this way their magnetic fields also will get cancelled out. Okay. So if you make circuits, you should try to make sure that, especially of course, the longer the wire, the more important this becomes. The current and the return path should be coincident as much as possible. Okay. So essentially, you should not have current loops with large areas. If you have current loops with large areas, they will radiate out magnetic field. They'll also be susceptible to magnetic field. We also know that what is Kirchhoff's voltage law? What is, I mean, there is some approximation there, right? How do you derive Kirchhoff's voltage law? Do you know? How do you derive Kirchhoff's current law and Kirchhoff's voltage law? Kirchhoff's current law is basically no local charge accumulation, you have charge conservation. So anything that's coming in will go out, right? So that's why if you have a closed surface, there is no, I mean, whatever is coming in has to be going out. That is Kirchhoff's current law. What is Kirchhoff's voltage law? Yeah, will it add up to zero? What is it? What does it actually add up to? Hmm? What is where does it come from? All this, so what are the fundamental equations from which you derive all this? What's the fundamental set of equations from which you derive Maxwell's equation? So what is Maxwell's equations? That going around the loop, it is equal to something. What is it? What is it? There is a rate of change of magnetic field. If the rate of change of magnetic flux cutting the loop is small, then that is equal to, you neglect that and you make it equal to 0. But if you have a huge loop and then you have that integral of dou v by dou t, that's in the differential form. If the integral of this is not negligible, actually the sum of voltages is not 0. Okay. So this is how this is useful in a generator. You have rate of change, you have changing magnetic field and it induces a voltage. But when you are making a circuit and you want the voltage here to appear there, you don't want that to form a big loop, because then the voltage that appears here will be the voltage that you apply here plus whatever is the result of changing magnetic field. Okay. So you should keep the loop area to be as small as possible. That's why they make wires like this, in which one wire is basically inside the other, right? There is a shield and so on, so that it doesn't take in any magnetic field interference, right? So this is important, but anyway, in our case, basically this is just motivation for using fully differential circuits. And in general, all these problems get better if you make things smaller. Okay, that way ICs are anyway better, because everything is small, everything is compact. All this will become worse when you have larger, physically larger connections and areas and so on. Okay. So we will use fully differential signals and circuits. Fully differential signal means every signal is represented on, you use two wires to represent every signal. Also, with respect to the common node, the two wires will carry equal and opposite voltages or currents. Okay. So that means that your circuits also, any circuit that you have, there will be a common ground, but the circuit itself will be symmetrical about some line. Okay. So that means that the upper half of the circuit and the lower half of the circuit will be exactly the same. Okay. And you have fully differential input, fully differential output. Okay. So now when you have fully symmetrical circuits, right, there are shortcuts to analyzing them. It's not quite a shortcut. Actually, if I didn't give you all this motivation about fully differential stuff, you could think of it as some circuit with two inputs and two outputs. How many possible transfer functions are there? 4, from here to there, there to there, there to there, and there. Okay. But because of symmetry, some of these become redundant. Okay. And functionally, what you want is from the differential to the differential one. Okay. So now when the circuit is also fully symmetric and you have either fully anti-symmetric excitation, that is differential excitation, or symmetric excitation, that is common mode excitation, there are shortcuts to analyzing them. Okay. So again, I think this is very basic circuit stuff, so I won't spend too much time on it. So a fully symmetric circuit, that is, what does it mean? You have two identical circuits, okay, and they have some corresponding nodes, let's say, right? Now, even if the circuit doesn't apparently look like this, if there is some common stuff, you can always split them into two parts, right? If you have a resistor, you can just split them into two resistance of double the value in parallel and so on, and assign it to each. And there can be connections between them, and there can be connections to ground from both sides. They are also symmetric. Okay. Now, In general, you can put any voltage there and any other voltage there, but we will assume voltages of this form. Fully differential, or let me just call that. This I have mentioned before also, because our interest is in differential signaling. Any signal that we have, V1 and V2, instead of taking them as arbitrary voltages, we resolve them into the differential and the common mode components, where Vd is V1 minus V2 and Vcm is V1 plus V2 divided by 2. Okay. So we always analyze them. We can analyze them with either V1 and V2 or Vd and Vcm. We'll do it with Vd and Vcm because that's what is functionally significant for us. Most of the time we want the circuit to react to Vd but not to Vcm. Okay. So now let's say we take this case where we have fully symmetric circuit with symmetric excitation, that is common mode excitation. What simplification can you think of here? I mean, the two circuits are the same. The input applied to the two sides is the same. So what do you expect in the solution, the circuit solution? The corresponding node voltages here and there will be, okay, and the currents flowing through these wires will be 0. Okay. In fact, you can imagine that by first removing these wires, right, and then you will get some solution to these two. But of course, the voltage here and there will be the same. Then you connect them, nothing happens. Okay, so no current will flow. So you can analyze this by just cutting off those wires and analyzing only the half circuit. So this is the common mode half circuit. Essentially, you open circuit the connections between the two halves. Okay. There's one more way to think about it. The two sides are the same, so you can just flip them on top of each other and basically you double all the components. That will give you the same voltage solutions. The currents will be double, but we'll just call this the common mode half circuit, just as matter of convention. Okay. Which one? Yeah, right, but they're still corresponding to each other, right? So yeah. I mean, basically all those four nodes will have the same voltage in that case. Okay. I have to think about if there's some exception. Which circuit are you thinking about? Any particular circuit? Okay. Let me think about it. Yeah, I think then it's like shorting all four, I believe. So this is the common mode half circuit, right? Now, I have not used any linearity arguments here. So this common mode half circuit is actually valid even for nonlinear circuits. Only thing that is required is symmetry, because if these two halves are identical, you apply the same input, they will give you the same circuit solution. That is true for whether I mean that is true for linear and nonlinear circuits. Okay. Now the other one, for the differential case, what happens? So now you can use superposition. If you do that, of course, by saying superposition, I am assuming linearity here. If I set this to 0, I will get some solution because I have Vd by 2 there. If I set this to 0 and put Vd by 2 on this side, I will get the same solution. Now I put minus Vd by 2, I get exactly the opposite polarity solution. So when I add them up, these node voltages will be 0. Okay. So if you have a fully symmetric circuit with anti-symmetric excitation, nodes along the center line, nodes along the line of symmetry will have 0 voltage. So you can just short them to 0 and do the analysis. But this has assumed both, this has assumed linearity and symmetry. Okay. So this part is true only for, okay. So then your differential half circuit would be only that much. So in a way, you can think of it as fundamentally you have not saved anything. Instead of analyzing the full circuit with 2 inputs, you first do the common mode half circuit with only common mode input and differential half circuit with only differential input. So that way, overall it may be the same. But the point is this is more functionally significant. Okay, you know how it behaves for differential signals, which is the desired functionality, how it behaves for common mode signals. So this is how we typically go about doing it. And usually this differential half circuit will correspond to some other single-ended circuit that you already know, like a common source amplifier and so on. Okay. Any questions? So hopefully you are able to do the assignment, because the assignment is basically this, that's all. You don't have to worry about what circuit it is, you just have to do the analysis. So now we'll go about converting the op-amps that we have into fully differential op-amps. Okay. Because finally we'll be making fully differential everything. The amplifiers will be fully differential, etc. Now, we use the op-amp in a feedback loop. If every op-amp has 2 inputs and 2 outputs, again, you can imagine that there are 2 feedback loops. Again, we don't think of it as 2 independent feedback loops for each voltage. We will think of that as a differential feedback loop, which will give you the function that you want, amplifier, filter, whatever it is. And then a common mode feedback loop, which will make sure that the common mode response is 0. Okay, that's the idea. So ideally, in a fully differential circuit, everywhere you should have a signal and its opposite in the counterpart. Okay, voltages or currents. That means that necessarily the average value or the common mode value will be 0. But that has to be enforced through a separate feedback loop that is called common mode feedback. Okay. So now we will need to introduce, first of all, we have to turn our op-amps into fully differential topologies. That part is not very difficult. And we'll have to introduce common mode feedback so that the common mode response is 0. Okay. So we will look at all of those things. And then and then we'll look at the common, because of that we need to study common mode feedback circuits as well, and common mode impedance, etc., right? Now everything that you know about negative feedback will come in handy there as well, because that's yet another feedback, but only for the common mode. Okay. So all the circuits that we have so far, the single stage op-amps and the 2-stage op-amp and so on, can be converted to fully differential versions. Now the circuit will look more complicated initially, but first of all, you will find that the frequency response is actually better in some ways compared to the single-ended op-amps, okay, which are asymmetrical. So what aspect of the single-ended op-amp frequency response was because of asymmetry? Do you remember? There's one particular thing that was because of asymmetry. What was it? Yeah, that pole zero doublet, right? Because one side was going through the parasitic pole, one half of the current, the other one was not. Such things will not be here because it will be fully symmetric. You don't have that extra pole zero in the fully differential op-amp. So overall, the fully differential stuff will be better. So, and of course, it's the it's very commonly used in analog IC design. So that's something that you have to learn. But whatever you know about single-ended feedback loops will be helpful, because if you look at just the half circuit of the fully differential circuit, you will get single-ended circuits. Okay. Any questions? So finally, the motivation for using fully differential signaling and fully differential circuits is that they are less susceptible to garbage. They also put out less garbage in terms of signal. So they don't interfere with each other as much. So the performance will be a lot better. Okay. So all high performance ICs will be fully differential. Any questions? Okay then. See you.